Moment-generating functions are a powerful tool in probability theory. A moment-generating function uniquely characterizes a random variable's probability distribution. For a random variable x, the moment-generating function is defined as the expected value of e to the power of t times x. For continuous random variables, this is the integral of e to the power of tx multiplied by the probability density function. For discrete random variables, we sum e to the power of tx times the probability mass function over all possible values. The moment-generating function gets its name from its ability to generate the moments of a distribution. When we differentiate the MGF n times with respect to t and evaluate at t equals 0, we get the nth moment of x. The first derivative at t equals 0 gives us the expected value or mean of x. The second derivative at t equals 0 gives us the second moment, which can be used to find the variance. Let's examine three key properties of moment-generating functions. First, the uniqueness property. If two random variables have identical MGFs, they must have the same probability distribution. Second, for independent random variables, the MGF of their sum equals the product of their individual MGFs. Third, for a linear transformation y equals a x plus b, the MGF of y relates to the MGF of x as shown. To visualize the power of moment-generating functions, let's look at the normal distribution. For a normal distribution, the moment-generating function has this elegant form. As we change the parameters of the distribution, both the distribution shape and its MGF change. It's important to note that moment-generating functions exist in a neighborhood of 0, though not all distributions have MGFs that exist everywhere. For example, the normal distribution's MGF exists for all values of t. The exponential distribution's MGF only exists for t less than lambda. And some distributions, like the Cauchy distribution, don't have an MGF that exists at all. Moment-generating functions have several powerful applications in probability and statistics. First, they provide an elegant way to derive moments of distributions without requiring complex integration. Second, moment-generating functions significantly simplify working with sums of independent random variables. Third, they're particularly valuable in proving important results, like the central limit theorem. Let's look at the normal distribution as our first example. The moment-generating function of a normal distribution with parameters mu and sigma squared is exponential of mu t plus sigma squared t squared over 2. To find the mean of this distribution, we differentiate the MGF with respect to t. Then we evaluate this derivative at t equals 0. This confirms that the mean of the normal distribution is indeed mu. One of the most powerful applications of moment-generating functions is simplifying work with sums of random variables. If x1 through xn are independent random variables, then the moment-generating function of their sum equals the product of their individual moment-generating functions. In the special case where the variables are also identically distributed, the MGF of their sum is simply the MGF of one variable raised to the power n. Let's examine the moment-generating functions of several common probability distributions. For a Poisson distribution with parameter lambda, the MGF is exponential of lambda times e to the t minus 1. For an exponential distribution with parameter lambda, the MGF is 1 divided by 1 minus t over lambda, valid for t less than lambda. And for a binomial distribution with parameters n and p, the MGF is the quantity 1 minus p plus p times e to the t, all raised to the power n. Now let's visualize how distributions change as their parameters change. Moment-generating functions help us understand these transformations. As parameters change, the distribution transforms, but its moment-generating function always maintains the form shown here, making it a powerful tool for analysis.